Hello. Hello, good afternoon.
Good afternoon, sir.
So, what we did last class? I think concentration cell, no?
Yes, sir.
The last part. Okay. Okay, just a second, we'll start. Okay, guys. So, I think last class we have finished electrode concentration cell, correct?
Yes, sir.
Yeah. So, the other one, that is electrolyte concentration cell, that also we have discussed. Okay. But quickly, I'll just write down the cell equation or no, Nernst equation for that. Okay, so electrolyte concentration cell is what? Oh, I did not share
So
this.
the electrolyte is the same.
Electrode concentration cell, we have discussed that the pressure or concentration of electrode will be different, right? So in electrolyte concentration cell, the concentration of electrolyte in the two half cell will be different. Concentration cell, whenever we have, it means we have same electrode both side, and hence the E0 cell is always 0 for concentration cell, correct? Okay. So now you see the second type we have, that is electrolyte concentration cell. Okay. So like I said, for this one the condition is E0 cell is again 0. Concentration of electrolyte in the two half cell is different. Are you solving questions based on this, like on electrochemistry?
Yes.
I am asking all of you, please reply. Okay. All of you are solving assignments, right?
Yes, sir.
Okay. So yesterday I have shared one question on the group, like on that other group. I know some of you are not there in the group, but those who are there in the group, why didn't you solve those questions? Did anyone try? If not, then you try that question today. Okay, after the class. Huh?
I tried.
You did not get.
So I got it, but I'm not very sure.
So you should have told me no. Whenever I post some question, you should at least give it a try. Okay, whether you get it or not, that's a different thing. Okay, so take care of one thing. Okay, if you have tried, you should have texted me, like you can text me personally also on my number, right? So this is what I did. I did not get it. Yes. So yes. So when you get time today after the session, you must try that question. Yeah, all of you. Anyways. So but the assignment that is there on the learnist, okay, you must solve those questions, all of you, okay? Because again, I'm telling you, one question you are definitely going to get from this chapter. In fact, there are 5 chapters of physical chemistry. One question you will definitely get. Okay. So out of 25, if 4-5 questions you are getting from this 4-5 chapters, that's a very big number out of 25. Okay. So don't take this lightly. Okay. It's very important. Okay. So this is the thing we have. Concentration of electrolyte in the 2-half cell is different, right? 2-half cell is different. Okay. So for example, you see, if I take an example of it, I can write PT H2 at certain pressure, right? Then we have phase boundary. We'll have some electrolyte here and some concentration, suppose C molar, then salt bridge, electrolyte with different concentration we should take. No, so it is C1, or anode, so it is Ca. It is cathode, so CM, phase boundary, and then H2 with the same pressure, and then platinum. This is the electrolyte concentration cell we have. Okay, so again we'll do the same thing. We'll write down the cathode reaction. Okay, we'll write down the anode reaction, and we'll add the two to get the cell reaction, and then we'll apply Nernst equation into this. Okay, so quickly I'll write down the cathode is this. So the reaction of cathode we can write 2H plus right, and the concentration of H plus is what? It's same, concentration is same, right? So we'll let it be as it is. Plus 2 electron converts into H2. Acha, concentration of H plus is Cc here, and this is P. Okay. Another one is H2 with the same pressure. It converts into 2H plus. Here the concentration is Ca plus 2 electron. So when you add this, you'll get the cell equation. Cell equation, which is 2H plus concentration Cc gives 2H plus concentration Ca. Correct? So when we apply Nernst equation into this, E cell, E naught cell is 0, minus 0.0591 divided by 2 log of Ca by Cc square. Is it correct? Right? So this is further 0.0591 by 1 log of Cc by Ca. So for feasibility of this reaction, what is the relation of Ca and Cc?
CC greater than C.
The concentration at cathode must be greater than the concentration at electrode. This is the relation we have for feasibility of this reaction. Clear? Okay. Now you see some questions onto this. Yeah, Pradyut, I'll send you. Okay.
Okay, sir.
This question you see. Try this question. See, you might have some calculation into these kind of question, but you don't worry with it, okay? Because you see, it is asked in 1998 JE, right? So that time you have they were like they take subjective questions, right? So there are so much of time, so they give calculation like that only, okay? My point, like my why I'm giving you this question, so that you can understand the concept. If you're getting very complex calculation, you can use calculator for that. Vikas, are you there?
Yes, sir.
Did you get the answer of that question?
I didn't see, sir. I was doing maths in the morning.
Okay, you try that once. I think you have written the reaction reversed. It should be Ag plus Cl minus gives AgCl.
Okay, sir. So I'll see you.
Okay, I think that is the mistake. Try that once, okay? After the
Yes, sir.
class. Should I do this?
So almost done. Just careful.
Could you tell me what is the E naught value for this?
0.
0. Why it is 0?
Concentrations are there.
Because it is a concentration cell, and you see it is not written in the question, right? So you have to identify this. We can see the electrode are same in the both half cell, so it is a concentration cell. So first of all, we can write E naught cell is 0. What we need to find out?
So
We
1
need to
minute.
find out the, sorry, okay, you
So
are
can
trying.
you, yeah.
Okay, fine. Answer, Richard. Richard Singh, what is the answer? Okay, 4.1 into 10 to the power minus 0. That's not right. Okay,
So
see
I
this.
got 10 to the power of 2.7.
No. See, I'll do this. First of all, the reaction of anode is what? Ag solid converts into Ag plus electron. Okay, and cathode reaction is what? This is the concentration of this at anode. See, we do not know this concentration. And from where this Ag plus is coming? This Ag plus is coming from this salt, Ag2CrO4. So we have actually the anode half cell. We have some electrolyte present here. We do not know about that electrolyte, what electrolyte is present. But since the half cell must contains the ions of this rod of the electrode, so to have this electrolyte for Ag plus present here into the solution, what we have added? We have added Ag2CrO4 salt into this, so that it dissociates and provides Ag plus ion into this electrolyte, right? And Ag electrode is present into this. So this is the arrangement of the anode half cell. We have an electrolyte, and in this salt is present, correct? So in this electrolyte, the Ag plus ion that is present here, it is because of the dissociation of this salt, first thing, right? So if you find out the concentration of this Ag plus, then we can find out the concentration of the other ion into this, because when this dissociates, it gives what? It gives 2 Ag plus CrO4 2 minus. No, it's not here. Okay, so this is the, if you know this concentration, the molar ratio is 2:1. Half of the concentration of this is the concentration of CrO4 2 minus, and hence we can find out Ksv. Did you understand the concept here? Right? Okay, so this anode is this. Now cathode reaction, if I write down, the reaction of cathode (10 to the power minus), I think it's close actually, 2.85 you have taken. The answer is 2.28 into 10 to the power minus 12. So it's correct. Okay, we can take that approximation. Okay, anyway, so wait. So this we have. Now the reaction at cathode is what? Cathode reaction is Ag plus electron converts into Ag solid. This concentration is given 0.1 molar. You don't have to think about it, right? When we write down E cell is equals to what? E naught cell will be 0 because it is a concentration cell. 0.0591 divided by 1 log of what we should write? We should write this Ca divided by 0.1. Okay, Ca divided by 0.1. Now this E cell is
the value of N1 over here, because in the, like, on the anode side, aren't we getting 2 Ags for every dissociation?
That, see, I am just taking total concentration of Ag plus is 2. If you multiply this by 2, that also we can write, okay, but that won't change the answer, because you have to balance the equation, right?
Yes.
So
sir.
here also we have a square of it. If it is 2, this 2 and square will get cancelled.
Okay.
Not make it, but if you write this, it is not wrong. Point is, when you add the 2, the electron must get cancelled. Okay, when we write down the dissociation of this, then we'll write 2Ag plus CrO4 2 minus. But here in this reaction, what I'm trying to represent here, that Ag convert into Ag plus and 1 electron is going out.
Okay, sir.
Correct? Understood? Because you see what happens. This is the metal atom is dissociating. No, it's converting into ion. So this Ag won't convert into 2Ag plus. Are you getting it? This is metal atom. It converts into Ag plus only.
Yes, sir.
Okay.
Yes.
So that's the thing. So, but if you write this also, you will get the same answer. But anyways, E cell is given, which is 0.164, and Ca we can easily find out from this, which is 0.0591 by 1 log of 0.1 by Ca. Now you can use calculator and find out the concentration of A here. Okay. So this concentration that you get, Ca, is equals to Ag plus concentration on the anode side is equals to 1.66 into 10 to the power minus 4 molar. This is the concentration you get here, approximately. Okay. Now one thing you don't, for this salt, if I write down the expression for KSP, could you tell me what we get the expression here for this salt, KSP expression? If it is S, solubility is S, so it is 2S and it is S, right? So it is KSP is equals to
Ca
Ag plus,
divided by
yes,
4.
Ag plus square into S, right? Into CrO4 2 minus. So is this 2S square into S? Is it?
Yes, sir.
What is the value of S?
So it's just this 1.66 thing divided by 2.
No, it is not S. It is 2S.
Yes,
Because you see,
That
divided.
thing divided by 2.
Yes, sir.
S is this divided by 2.
Yes, sir.
Okay. So don't make this mistake. Okay. 2S value is this because it is the total concentration of Ag plus. Correct. It is not like the solubility. It is not S. It is the it is a concentration of Ag plus in the anodic half cell. And that is equals to 2S because we assume that all the Ag plus is coming from the salt. Correct?
Yes,
Yeah.
sir.
So we can write down the relation, the concentration of Ag plus, the molar relation that we have is equals to what we can write? Oh, half of this, what? CrO4 2 minus. Correct. So this expression I'll write down. I won't write this in terms of solubility. Probably you will get confused. So I'll let it be the solubility things we don't have to find out. We have to find out solubility product. Okay, so this will be what? CrO4, we can substitute this and this becomes half of Ag plus concentration Q, and then we can substitute this. Yes or no? So answer is half of 1.66 10 to the power minus 4 cube. This is the KSP of this one. Did you understand this?
Yeah, I did it in a different way and got a different answer. So I said
What?
E cell. So I did it in a different way, but I got a different answer. So I said,
What did you do?
so I did delta G is minus NF E cell, and delta G is also minus 2.303 RT log Q. And then I found Q from there.
Delta G is minus NFE cell, and that you substituted as
Minus 2.303 RT log Q.
RT log K. Okay. So what did you get over there?
I got concentration is 0.30
Concentration of what?
Ag plus from the salt.
No, see, when you have taken delta G is equals to minus 2.303 and ln something, it means you have assumed the reaction is at equilibrium. Then only it is possible, no?
Yes, sir.
Delta G, you are substituting 0. Then delta G naught is equals to what? Minus 2.303 RT log K. Right?
Yes,
So
sir.
that equilibrium condition you cannot assume.
Okay, sir.
Right? I'll show you one question where you have to use this delta G. When we have this method, okay, I'll show you one question on that. Okay, today only we'll show you. So this is, we cannot take delta G is equals to 2.303 RT log K over there. Okay, because equilibrium is not there, equilibrium condition is not we are taking. So basically can find out the solubility, we can say, or the solubility product of any salt present in any of the half cell with the help of E cell of the reaction, electrode potential of the reaction, correct, of the cell. Okay, so that is how we can find out. You see this in J, this was asked in JE, and this kind of question where we have solubility product and each cell, they have asked many times in JE exam. I can show you many questions on this. Okay, when you solve questions of this, you'll get this kind of questions very frequently. Okay, could you find out this one? Vikas, could you send me the working of your last question?
Yes, sir. Yes, sir.
Done. See, equilibrium constant we need to find out. So delta G is 0. Delta G naught is equals to 2.3 minus 2.303 RT log Kc. No, no, that's not the answer. Varun, what is your answer? See, this one is simple. You just need to do this. Delta G naught is equals to minus 2.303 RT log Kc, and this is what we need to find out. Okay, Kc. Delta G is equals to what we can write? Minus NF E naught cell divided by 2.303 RT log Kc, right? So 2.303 RT by F is what? RT by F is 0.059. Okay, so we can write this negative sign, and this negative sign will get cancelled out. One N value is 1 divided by 0.0591 into E naught cell is equals to log Kc. Is it right? Because 2.303 RT by F is 0.0591. Okay, E naught cell is what?
0.76.
0.76. So this is oxidation, ion is oxidation, and this is reduction, right? So 1.44 minus
Yes, sir.
E
More
cathode
I-
minus E anode.
I did the same thing, sir.
So what is the answer you're getting?
So is it
I got 7 into 10 power 12-ish.
Yeah, 10 power 12, whatever.
7 into 10 power 12 is correct, 7.6.
So that's what I sent.
Oh, yeah, I didn't see that actually. Okay,
Oh,
1
okay.
by
Oh, sir, I forgot to send the into
0.091
7.
into log Kc. So again, I'm telling you this anti-log value will be given in the question. Okay, you don't have to worry about it. Okay, 10 to the power 12, this is the answer. Delta G expression directly with you.
So here we can get the same thing by saying E cell will be 0, right?
That's how we get this.
Yeah,
E cell is 0. E
So like,
it is at equilibrium,
yeah.
so delta G is 0. Delta G is 0, so E cell is 0.
Okay, sir.
And then we'll get this. Same thing.
So over here, if you approximate 0.0591 as 0.06, then it
Yes,
changes
you can.
7 point. So it changes from 7.6 to 4.6.
Is it?
Yes, so it's a huge difference.
So we won't take that.
Yes.
See, the exact value is this. This is only we take. Sometimes in objective question, what happens? That options, there's a huge difference in options. And you will observe that if you take 0.06, the calculation is quite easy. Okay, so in that case, we can assume that. Right? But this one is, you see, this is subjective questions. And that time they have 2 exams. One is screening, other one is mains. So this is the mains exam. In mains, they ask the subjective questions where you have to write down the answer in up to 2 or 3 decimal digit, exact calculation. So you cannot approximate that. But nowadays, they're asking objective questions, multiple choice questions. So based on the calculation and options given, you can take that approximation. Got it?
Yes, sir.
Okay. So this we haven't done now. We'll do this. This is also we won't do now. This one you try. I think this one you can do. minus 0.22. Yeah, minus 0.22 is correct. Exactly correct. Exact value it is. Minus 0.22. Okay. So here you see KSP of CuOH whole twice is equals to concentration of Cu2 plus into the concentration of OH minus square. Okay. E naught value is given 0.34. Reduction potential we need to find out for pH is 14. Okay. KSP is given. This KSP is 10 to the power minus 19. Right. So we cannot consider this as S into 2S, then you find out solubility of this. This we cannot do here because in the electrolyte in the solution, we do not know whether there is H plus or OH minus present or not. Because this KSP is true when this is present in any electrolyte where there is no common ion effect possible. But here the pH is mentioned, it means the OH minus concentration is also known in this here, right? So with that, what we can do, we first of all calculate the OH minus concentration and that we substitute over here and then we'll find out the Cu2 plus concentration. Why? Because to find out the reduction potential, that is E Cu2 plus to Cu, this will be E naught, that is 3.34 minus 0.0591 divided by 2 log of 1 by Cu2 plus. This Cu2 plus concentration we need to find out this E value, right? Electrode potential value. This Cu2 plus will find out from KSP, right? So KSP is 10 to the power minus 19. And since pH is given 14, so POH is what? POH is 0.
0.
It means OH minus concentration is what?
1.
1. OH minus concentration is 1. So Cu2 plus concentration is what? 10 to the power minus 19. Cu2 plus concentration is 10 to the power minus 19, which we substitute here, and then we'll solve it. We'll get 0.22 volt answer. Correct? Yeah. Yeah, all of you have got the correct one into this one. So remember here, we won't use find out, don't think about it, that with this KSP, we'll find out solubility and then Cu2 plus concentration, right? Solubility here won't be the ideal, it is not the ideal case because we do not know about the electrolyte. There may be some common ion effect, so because of that, the solubility may decrease. Okay, one more question we'll see. See, this the quality is not that clear, but still we can manage. See this one. Are you able to see this?
Yes, sir.
Try this. Done?
Is it around 5 in a 10 to the power minus 11?
Yes.
Is it B?
Option B, right?
Yes, sir.
Okay, that's right. What is like? What did you do?
So we know that the concentration of chlorine is 0.1, and then E naught reduction is 0.8, and
Hmm.
E reduction is 0.25. So then minus of that, so minus 5.5 is minus 0.591 log 1 by concentration of silver. So then you get concentration of silver, and then you multiply that with chlorine.
What is the cell reaction? Can you tell me?
So it's just Ag plus electron is Ag.
Correct. See, actually, this question is, it is like the method you have done is not right for this question. Okay, but answer that you have got, that is correct. Okay, so that is just a coincidence that from the wrong method you are getting the correct answer in this. But you see, this is the case of metal and metal insoluble salt. If you look at your notes where I have discussed about metal and metal insoluble salt, half cell, different types of half cell, there I have discussed metal and metal insoluble salt, right? So because this AgCl is getting precipitated, right? So it is insoluble salt. It is not soluble. The previous one that we have done, Ag2CrO4, the first question, that was soluble, right? So when we have metal insoluble salt, then we'll use the concept of delta G to solve this kind of question. Okay, delta G to solve this kind of question, right? And since it is the concentration cell, so E naught value will be 0, right? So delta G naught won't be 0, E naught will be 0, right? Delta G will be 0, E naught will be 0, not delta G naught or E naught. So this one, you see, the cell reaction here we have, see what method you have done that you know already. Okay, so the reaction at anode, oxidation reaction, and this reaction is Ag, which is the electrode, and Cl minus, right? Because it is an electrolyte, ion present into the electrolyte, and it forms what? AgCl, salt plus electron. This is the reaction at anode. Cathode reaction is the reduction reaction, and Ag plus aqueous reduced into Ag. That is Ag solid. This is also Ag solid, Ag solid. This is the reaction at cathode. This is the two reaction. Now you look at this question. This value is given. What is this value? This value is E naught and E naught of Ag to Ag plus. But this is Ag plus to Ag. This E naught value is plus 0.799 volt. No doubt. For this one, Ag plus and Cl minus, okay, the silver will dip, our silver wire dipped in this molar solution saturated with AgCl develops oxidation potential this. So for this, the oxidation potential given, that is E value. It's not E naught, it is E value. It is given minus of 0.25 volt, right? Silver wire dipped in the HCl solution, which is saturated with AgCl, right? So we'll get this. But the net cell reaction is what? See, the net cell reaction is the addition of these two. Is the addition of this two, and that is Ag plus Cl minus converts into AgCl. Did you get it? Did you get it? Yes. Yeah, I know you'll get option B, but have you done this method? Because this is the one which we should use. Did you understand this? So this is the net cell reaction we have, and for this KSP we need to find out. Yes, correct. So just try to understand this. KSP we need to find out. So could you tell me what is the E naught value of this? What is the E naught value of this?
You have to use delta G.
What?
You have to use the delta G formula I'm getting.
Delta G formula. So first of all, you see that again there is one more catch here. Here it is E naught given, but this is not E naught. It is reduction. It is oxidation potential, not a standard value. So from this, first of all, you need to find out the standard oxidation potential of this. Are you getting it? So what we'll do, we'll apply the Nernst equation here. So E is equals to E naught of this reaction minus 0.0591 by 1 log of what we should write, 1 by Cl minus. From this, we'll find out E naught first, because E value we know it is minus of 0.25, right? Cl minus concentration is 0.1.
Plus 0.25 because that's the oxidation potential.
That is what in the question it is given, minus 0.25.
So, but that's oxidation potential. Here we're using.
It is what, this is what given in the question also, oxidation potential, and this is oxidation reaction.
Okay.
Yes, it is the oxidation potential given in the question, and this is the oxidation half only. That's why I've taken the same value with the sign.
Yes, yeah. Sorry.
Correct, no? So from this, if you substitute E and Cl minus, you'll get E naught as minus of 0.1909. You can check this. You'll get this. Did you understand? If you understood this, it is done then. Then after this, you know what to do. Did you understand till here? Why we need this Nernst equation? Because this is a standard value and this is not the standard one, right? So we have to find out the standard value first for this half reaction, correct? Now, the next step will easily find out this delta G1 naught. We'll find out delta G2 naught. Then we'll find out for this reaction, we'll find out delta G naught, which is the addition of the two, delta G1 naught plus delta G2 naught. Okay. Now this we can write as, after this, it is 2.303 RT log KSP, because that is what the equation we have. For this equation is KSP only. This will be equals to delta G1 naught plus delta G2 naught. Now when you solve this, I'll write down the expression here. You can check this. Log KSP you'll get minus 10.289 approximately. And that you can easily write minus 11 plus point minus 11 plus point
711.
What?
So minus 11 plus 0.71.
71, right? Correct. So 0.71, you take it as 0.7, right? And 0.7, what is the value of log there? You see, I'll just do this. Wait.
5.
See, the value is this log, because this value they won't give you. The value which we can find out, they won't give you. So log KSP is what? We can write minus 11 plus 0.71. Correct? Is it right?
Yes, sir.
Right. So approximately 0.71, we can take it as log 5, because log 5 is 0.70. So approximation, we have taken this. Now this becomes log 5 into log of 10 to the power what? 11. We can write this becomes log 5 into 10 to the power 11, and hence KSP is what? 5 into 10 to the power minus 11. So approximately the answer is B. You see, there are so many things we had to do in this question. If you directly apply Nernst equation also, then you'll get approximately B as the answer. But you always keep this in mind, since the reaction is metal insoluble salt. So in case of metal insoluble salt, we have to use the concept of delta G. First of all, you write down the net equation, okay? And then correspondingly, you have to do all these things. Did you get it? Just look at this once. If you have any doubt, just tell me. Okay, insoluble salt, Roger, I'll send you some more questions on this. Okay, let us move first. Okay, we have to discuss so many things. I'll send you some more questions today only. Okay, because I'll check where it is. Like, I have to see. There are very few questions on this, but important. Understood, all of you? Right? I think the major problem that you feel is to write down the reaction. If you write down the half reactions, then you can get the answer. But like this also, you see, you did not know about what the cell reaction is. But unfortunately, somehow you got the answer because the data is like that, right? So it is just a coincidence that with wrong, equation or reaction, you got the right answer. Okay, but must understand this. We use this delta G value in case of metal insoluble salt. We are not using Nernst equation into this, right? If metal soluble salt is there, the first case Ag2CrO4, there we can use Nernst equation directly. But in case of metal insoluble salt, we use the method of delta G. Okay, fine. So let's discuss the other part. And this one is easier. The other part that we are going to do is electrolytic cell. Write down. Um, write down the heading. Electrolytic cell. See, what is an electrolytic cell here? One brief discussion of this, and then we'll see the terms one by one. In electrolytic cell, what happens? We have a construction like this, in which the the two electrodes are present. Two electrodes present this way, right? And there are electrolyte present here in this. Electrolyte present. So obviously when we have electrolyte here, so we have some positive charge ion and negative charge ion, right? So what happens here, since electrolytic cell, electrolysis takes place here. So electrolysis takes place here, and electrolysis is possible when you connect this with an external voltage source, right? External voltage source. So what happens, first of all, we provide current, right, into this system, right? So when you provide current into this rod, which is connected to the positive end of the battery, becomes the positive charge electrode because it is connected to the positive end, and this is the negative charge electrode connected to the negative end of the battery. From the positive end, current enters into the electrolyte, and from the negative end, current comes out of the electrolytic solution. The electrode which is positively charged or connected to the positive end of the battery, or through which the the current enters into the electrolytic solution, that electrode we call it as anode. So here you see anode is positively charged. This one is cathode, negatively charged, right? So what happens here, you see,
Sir, but like if the electrons are entering the
not
oh wait,
current,
electron flows out. Okay.
current, not electron. What?
Got it. I am so electron flow is opposite direction.
Opposite, yeah, right. So when you connect this battery to the external voltage source, the electrode becomes charged, and this electrode, in this case, it attracts the opposite charge ion towards its side. So negative goes towards positive, positive goes towards negative. These ions moves towards the oppositely charged electrode, and at the electrode, the reaction takes place, oxidation or reduction, right? So here what happens, either the mass deposited on the electrode, or if some gaseous species forms, then gas evolves at electrode. Like suppose if Cl minus get oxidized, it converts into Cl2. So Cl2 chlorine gas evolves. If Zn plus 2 get reduced, it forms Zn solid. So this will get deposited onto the electrode. Understood this? So this process is electrolysis. Did you get it? Yes.
So the the negatively charged particles move to the anode.
Moves towards the positive charge anode, right?
So,
Positive charge moves towards the negative charge cathode. And once it reaches to that electrode, there at the electrode, oxidation or reduction takes place. So at anode, we know at anode always what?
oxidation.
Oxidation. Cathode always reduction. So in this two process, only two possibilities are there. What are the possibilities? Either some mass will get deposited onto the electrode, or some gaseous species evolves at the electrode. Did you get this? Right? So now the question that they ask, that what is the mass get deposited at electrode? What amount of gas evolves at electrode? Did you get it? Did you get it, guys?
Yes.
Okay. Now the point is the amount that get evolved or get deposited onto the electrode, that depends upon what charge you are allowing to pass through the electrolyte, right? Means what charge you are passing through the electrolyte, that will, that will actually explains that what is the amount is getting deposited or evolves in case of gaseous species. And charge is what? Charge we can write Q is equals to what? I into T, right? Because we are having here current. current is nothing but the flow of electron. So for t time, if these many electrons flows, then what is the charge flows? That will be I into t, right? So the amount that get deposited or evolved, that depends upon what is the current flowing into the electrolyte. Are you getting it now? Right? To get the idea of this, that what is the mass get deposited or gaseous species evolves, we have a law, we call it as Faraday's law of electrolysis. And you will get questions on this only, Faraday's law of electrolysis. Okay, so what is Faraday's law? How do we calculate the mass deposited or evolved? We'll see that, but first 2-3 terms we have, and that will write it down. Okay, so write down the first thing, electrolysis. Write down electrolysis. Write down it is the process of chemical decomposition of an electrolysis of an electrolyte. It is a process of chemical decomposition of an electrolyte when electric current chemical decomposition of an electrolyte when electric current passes through its solution. Okay. Yes, Richard, that's right. But battery potential, you won't get any question. It will like they'll mention this current is flowing. They won't ask you EMF related question here in electrolytic cell. Okay, fine. Electrolysis is this. So what happens here? We are providing electrical energy, and this electrical energy is converting into chemical energy. So what happens in this cell, electrolytic cell, electrical energy converts into chemical energy, and it is exactly the ulta of the previous one, where chemical energy converts into electrical energy. What is the other difference? Anode here is positively charged. Anode is positively charged. Positively charged, and cathode is negatively charged. Cathode is negatively charged. Theoretical questions they ask on this. Anode we can also define as the electrode which is connected to the positive end of the battery. We can also define this as the electrode through which the current enters into the electrolyte. Okay, cathode, how we can define? It is connected to the negative end, right? Reduction takes place and the current leaves the electrolytic solution from this electrode. All the three different way we can define this. Okay, this electrolytic solution, write down the next line, conducts electricity due to the movement of ions. Due to the movement of ions.
Wait, sir, could you repeat it?
The electrolytic solution conducts electricity due to the movement of ions. Done. Okay. Okay, before going into Faraday's law of electrolysis, we should know the product of electrolysis. Okay, so write down the heading electrolysis of some important electrolytes. So they'll ask question based on the product of electrolysis also. Important electrolytes like what gas evolves at anode, right, or cathode, like that. They ask this question. Okay, so it is a bit theoretical. Okay, you need to know this particular thing. You have to memorize this. Okay, however, you can have some idea that how the product is forming here, but there are a few examples where there is no other way. You have to keep this in mind. Okay, I'll send you the details of this also, the reactions and all, but few 4 or 5 important one we'll discuss it here. Okay, so this thing, first one, you see, when we have electrolysis of, write down, electrolysis of fused NaCl, and we are using platinum electrode for this, PT electrode. So fused NaCl means we have only 2 ions here. One is Cl minus and other one is Na plus. These are the only 2 ions present. So Cl minus will get oxidized. It converts into half of Cl2 gas plus 1 electron comes out. Na plus will get reduced and it forms Na solid. So what happens if in the cell we have Cl minus present? So this Cl minus will move towards the anode, Na plus will move towards the cathode, and here it gets reduced. Then this Na solid will get deposited onto this electrode. Cl minus will get oxidized, and here the chlorine gas forms, which evolves. Correct? So that is the thing. They'll ask you that what is the mass get deposited over here. That calculation we'll do later. But here the product of electrolysis is what? At anode, this reaction takes place, and cathode, this reaction takes place. So what is the product of electrolysis? Product of electrolysis is Cl2 gas evolves at anode and sodium metal deposited at cathode. Done. All these oxidation and reduction of these ions present into the electrolyte depends upon their electrode potential, reduction potential, and oxidation potential. Like the second example we see, if you take the electrolysis of aqueous NaCl using platinum electrode. So could you tell me what all ions are present here in aqueous NaCl? The ions are Na plus, H plus, and
H minus.
Cl minus OH minus.
Cl minus and OH minus. So now you see there are 2 negative and 2 positive ions. So this 2 negative ion has tendency to move towards the positive electrode. So they will compete with each other to get onto the anode and oxidize. Similarly, these two also competes with each other to get reduced, right? So here what happens, the one which has more reduction potential will get reduced. The one which has more oxidation potential will get oxidized. That is what we know, correct? But this oxidation potential and all, you cannot memorize, right? You cannot memorize the oxidation potential of all metals. That's why I said in the beginning that you have to memorize this. You have to keep this in mind. Okay. So the reaction, the possible reaction I'll write down. I don't know which one is taking place here, but the possible reaction is what? Na plus aqueous will get reduced and it forms Na solid. Other possible reaction is what? H plus aqueous will also get reduced and forms half of H2 gas. Okay, the reaction of this, because this H plus is coming from the water itself, so the reaction of this is also written this way: H2O plus 1 electron gives half of H2 plus OH minus. So these two are the same thing because H plus is coming from water. Okay, now which reaction takes place, that depends upon their reduction potential. Now the reduction potential of any solid, and I am giving you this value, it is minus 2.71 volt, and the reduction potential of this is what? Hydrogen, it is 0.
0.
So which one is more?
Hydrogen.
This one is more. It means this reaction takes place and this won't take place because it is more, it has more tendency to get reduced, hence this reaction is possible. So if they ask you for aqueous NaCl, which gas evolves at cathode, the answer is what?
Hydrogen.
Hydrogen gas. That is the product of electrolysis. Okay, understood this? So this is the reaction of cathode, right? So first of all, which reaction is taking place, that you cannot say if you do not know the reduction potential, and that you cannot memorize reduction potential of all metals. That's why this thing you have to keep in mind, that whenever we have aqueous NaCl, then this is the product of electrolysis we have. Similarly, you see, if I write down the reaction at anode, so again there are two reactions possible. Cl minus converts into half of Cl2 plus 1 electron, and OH minus converts into half of O2 plus H plus electron. Okay, one negative, we have 2 electron. Charge balance, no? 2 minus 1. So 1 negative, 1 negative. This is the reaction. Again, this OH minus is coming from water. So with respect to water, if I write down the reaction, H2O converts into half of O2 plus 2H plus 2 electron. Because it is neutral, so it has to be a neutral, so 2H plus and 2 electron. Okay, now if I write down the E naught value of this, and this is the oxidation potential, I am writing it down, minus 1.36. It is oxidation potential. And for this one, the oxidation potential is minus 1.23 volt oxidation potential. Could you tell me which reaction is possible here? Huh?
So the water one. H plus.
The one which has more oxidation potential. Okay, so this is possible and this is not possible, right? But actually what happens here, this reaction is not possible, this reaction is possible. And the reason for this is over potential. Now this is something which we cannot have any idea by looking at the reaction, right? Which we cannot have any idea by looking at the reaction. That's why I said in the beginning that this you have to memorize. What is over potential actually? There are two types of potential we have. One is the potential which is thermodynamically determined, and other one is which is experimentally observed. Means by depending upon the ions, types of ions and various other factors, right? We say that this ion will get oxidized or reduced at this potential. This is the potential for this. But actually, the reaction is not taking place at that particular potential, which is defined experimentally, right? It takes higher, potential to get reduced or oxidized, right? So that difference in the two potential, the potential which is experimentally determined and the potential which is observed, at which the oxidation or reduction is taking place. So one is theoretically defined, other one the actual value where the reaction is taking place, the potential at which the reaction is taking place. The difference between the two is nothing but the over potential, right? So over potential, by looking at the reaction, we cannot say, okay, we have here over potential, so this won't take place, this takes place. This is the experimental thing, right? That is why the product here, the aqueous NaCl, the product of the electrolysis is what? H2 gas evolves at cathode and chlorine gas evolves at anode. Okay, write down this definition of overpotential. Write down. It is a potential difference it is the potential difference between the reduction potential difference between the reduction potential, in bracket you write down, thermodynamically determined, between the reduction potential in bracket thermodynamically determined of half reaction, thermodynamically determined bracket close of half reaction, and the potential at which the redox reaction is experimentally observed.
Can you repeat the last part?
And the potential at which the redox reaction is experimentally observed. Right? Experimentally observed. Next line. Because of overpotential, the cell requires more energy than the energy required it is a definition of overpotential. Okay, I'll repeat it again. Just give me 1 minute. Let me finish this once. Okay, because of the existence of overpotential, the cell requires more energy than the energy required thermodynamically to drive a reaction. The energy which is thermodynamically required, more than that, the energy which is required here. Okay, so again I am repeating this. Overpotential is the potential difference between the reduction potential in bracket thermodynamically determined bracket close of half reaction and the potential at which the redox reaction is experimentally taking place. Okay, observed. Next line. Because of the existence of overpotential, or since I given you because of overpotential, the cell requires more energy. The cell requires more energy than the energy thermodynamically required. The thermodynamically required to drive a reaction.
So could
To
you
drive
repeat?
a reaction. The last line.
Yes, sir.
Because of over potential, the cell requires more energy than the energy required thermodynamically to drive a reaction.
Thank you, sir.
So basically, the theoretical value which is given that this reaction should take place at this potential, but actually the reaction is not taking place at that potential. It is taking place at higher potential. So that difference in the potential is the over potential, right? So here you write down the product of electrolysis is, I'll write down the overall reaction. You copy this down first. The overall cell reaction is NaCl in water, aqueous NaCl. It converts into Na plus aqueous and Cl minus aqueous. Okay. Reaction is H2O plus electrons. It converts into half of H2 gas plus OH minus aqueous. This is the second reaction. Another reaction is Cl minus aqueous converts into half of Cl2 gas plus 1 electron. This is the reaction we have. Now the overall reaction you see, if I add the all, see what happens. This Cl minus gets cancelled. Any other thing?
The electron goes.
Electron gets cancelled, right? And the reaction is NaCl aqueous plus H2O liquid converts into Na plus aqueous plus half of H2 plus half of Cl2 gas. Right, this H2 evolves at cathode. This you must remember.
What about the OH minus?
OH minus will also be there. I'll write down here only then. NaOH. NaOH aqueous. So the product of electrolysis is cathode and anode. Hydrogen and chlorine gas evolves at the two different electrodes. Write down electrolysis of aqueous H2SO4 using platinum electrode. Okay. So aqueous H2SO4 you see means we have H2SO4 and H2O. So what all ions are present here? H plus present, OH minus present, and SO4 2 minus. Correct. So at cathode there is no confusion here because there is only one positive charge species, that is H plus, and this H plus will get reduce, and will write H2O plus electron gives half of H2 gas plus OH minus aqueous. So one thing is for sure that at cathode hydrogen gas evolves. Okay. At anode we have two possible reactions. We have two possible reactions. Means the first one, when we have low concentration of H2SO4. When we have low concentration of H2SO4, H2O converts into 2H plus half of O2 plus 2 electron. So when the concentration of H2SO4 is very low, H2O get oxidized. Okay. At high concentration, SO4 2 minus get oxidized into half of H2O8 2 minus plus electron aqueous. This is the two reaction we have for aqueous
The
H2SO4.
electrons aren't balanced, right?
So
the electrons.
Half of S2O4, S2O8, 2 minus, it should be H2 plus, H2O8, 2 minus, here we have 2 electron there. Is it? No, 2 plus 2, 4 ho gaya na?
Shouldn't be
So
S2
we'll have
minus
2.
Okay.
H2. Is it
Yes.
fine? 2
Yes,
if
sir.
you write. Then this half will remove from here.
Yes, sir.
So it was correct in the beginning when we said.
No, but in the beginning there will be 3 electrons there.
Oh no, it was half. Now again, just multiply full reaction by 2. It's just same.
It's fine, I guess, no?
Yeah, it was correct in the beginning.
Yeah, that's right. Yes, yes, fine.
Right. So similarly, we have this kind of, electrolysis and its product is very important. Not very important, we should not say. But like this, they ask question in the exam. What is the product? What gas evolves at anode or cathode? Right, like this. Or what is the, what statement is true in the electrolysis of this solution? They'll give you 4 options that this will get oxidized, this will get reduced, oxygen gas evolves at cathode, anode, like that. They'll frame the options, right? So this is very informative. It's very theoretical. You cannot think, logically over there, right? If you can think only if you know the electrode potential, right, which goes well with some of the electrolytes. But when overpotentiation comes, that also fails, right? So eventually, there's no other way, but you have to memorize those things, right? So I have given you 2-3 examples of it. I'll share one notes with you. One page is there. I'll share that notes, that picture. There are almost 5, 6, almost 10 electrolytes, and its concentration thing is given, and it's the product of electrolysis is given, right? So that you must keep with you, write down the notes, keep with you, and revise it once, because you never know what question they are going to ask in the exam, right? So you cannot miss all these things also, right? So that's the one thing. Another one, product of electrolysis we have discussed. Now the next thing here, from
Isn't
which
the
you'll
oxidation state of sulfur +6 in both sulfate and S2O8 minus?
S2O8, no, 3 plus 3, 3. No, it's in S2O8 it is not +6. How it is +6?
So I drew the
Calculate in
structure of it.
7.
It
It
is a
can't be
peroxy.
7.
See, it's a peroxy acid. We have a peroxy linkage in S2O8 2 minus.
Yes, sir.
Both sulfur connected by two oxygen, means SOOS bond is there. Are you getting it? SOOS bond, and each sulfur atom has 3 oxygen.
So each sulfur has 4 oxygen atoms, right? So 2 double bonds and 1 single bond.
This is the structure.
Yes, it's plus 6 only, right?
2 plus 2 plus 2 plus 6 we are getting, and here it is 4 we have, so plus 6 we have here. Okay, so oxidation state is plus 6. Yes, fine. Oxidation state is plus 6 in both the ions, right? But see, the charge is balanced in the reaction. Even if you see the above reaction, H2O, right? What is the oxidation state of hydrogen there in H2O? That is plus 2, and here also it is, this side we have plus 1, correct? On this. Oxygen you see minus 2, and here it is 0, right? So this is the reaction. But here what happens, you do not check this sulfur, because this is, we are talking about the ion. This sulfate ion is getting oxidized into peroxy ions, peroxy acid it is. This sulfate ion is getting oxidized into this. In that way only it releases 2 electrons. So obviously the charge on sulfur atom will be same, but sulfate ion as a whole is it's oxidizing. That's why you see H2SO4 if you write. So what we'll write? We'll take this ion, no, minus 2. So this should be plus 2, so plus 1 on hydrogen, right? So this ion is getting oxidized into the sulfate ion. Peroxy disulfate also we call it as disulfate ion, or peroxy acid ions we also call it as, right? So this is the oxidation of sulfate ion. And since the charge is balanced here, you see 2 negative, 2, 4 negative here, 4 negative here, it means it has to release, sulfate ion has to release electron in order to convert it into this. That's why it is an oxidation reaction.
Okay, sir.
As a whole we are talking about. Okay, understood? So this is the, the various product of electrolysis we have that you must keep in mind. I won't say you can logically you can do all this, because the reason I have told you, electrode potential you can talk about, but then when over potential comes into the picture, that electrode potential concept also won't work. Okay, so best way is to revise these things. You will understand what product we can get. Okay, if you solve some questions also, you'll get this kind of question. Try to keep those questions in mind, that in this electrolysis this is the product we get. Okay, that is the only way you can do this. Okay, the another and the most important part of electrolytic cell is, write down, quantitative analysis of electrolysis. So in electrolysis, what happens? Okay, we so far we have understood that the metal ion gets deposited onto the electrode. So either the mass of the electrode increases by the deposition of metal ion onto the electrode, or some gaseous species involved in the reaction. Now we have to find out that what mass is getting deposited. Okay, what mass is getting deposited, or what amount of gas is getting evolved. That is the quantitative analysis of electrolysis. It's very simple and easy. Okay, It's the question based on this topic you should not miss. Okay. Electrochemical cell, you can say a little bit of trick is there. If you made some mistake in writing down the half cell reaction, the entire thing will go wrong, right? But here you should not miss the question, because it is very easy. You'll understand this in one shot. Little bit of idea you should have of equivalent mass. Okay, that is the concept we are going to use here. Okay, so the quantitative analysis is done by the scientist called Faraday. Okay, and hence we call it as Faraday's law of electrolysis. Write down. Faraday's law of electrolysis. Faraday has given two laws for this quantitative analysis: Faraday's first law and Faraday's second law. Okay, but if you understand first law, you can easily, there's no need to understand the second law, because it's a part of first law, right? That's why in some of the book they did not even give first law and second law. Just they have given Faraday's law of electrolysis and they explained everything. So based on the first law, we can deduce second law. Okay. So first of all, we'll see what is Faraday's first law. Write down the statement. The amount of any substance, deposited or liberated at any electrode is directly proportional to the quantity of electricity passed through it. Quantity of electricity passed through it. Can we say quantity of charge also here? More electricity means what? More charge, because Q is nothing but I into T. If I amount of current passes through the electrolytic solution for a time T, then what is the charge passes through? The charge is Q is equals to I into T, right? So electricity, and we can also say here charge. More amount of charge passes through, more amount will get deposited or evolved. Fine, simple, clear, right? You see the ions moves towards the electrode, right? So more charge, if you allow the current to pass through the electrolyte, more amount of current, then more ion will move towards the electrode, and once it reaches the electrode, there the oxidation or reduction takes place. So electrolysis will be more when the charge is more or current is more, correct? So according to first law, what we can write, W is the mass deposited, or I'll write M is the mass deposited, is directly proportional to the amount of charge passes through it. M is directly proportional to Q, where M is what? M is the mass deposited, or we can also consider this the mass evolved. Okay. Q is the amount of charge. Write down if Q, if I is the current, write down this. If I is the current, I ampere is the current, passes through the electrolyte, for a time t seconds, then charge q is equals to, we can write I into t. Here, if you remove the proportionality sign, we'll write m, the mass deposited, is equals to zq, where this z is the electrochemical equivalent. So constant electrochemical equivalent. Depends upon the metal. Okay, if metal is same, z value will be same, right? So further, what we can write, if you substitute q is equals to it here, this becomes m is equals to zit. Any doubt in this? Right? This is the only relation we have. Like I said, the second law we can easily deduce from this particular expression. Now, one note you write down here, and this line is VVI, very important, right? One note you write down, it has been observed that when 1 mole of electron, when 1 mole of an electron passes through the electrolyte, for 1 second, then the mass deposited for 1 second, then the mass deposited equals to the equivalent mass. Then the mass deposited equals to the equivalent mass. Correct? So could you tell me what is the charge on 1 mole of an electron?
96,500.
Charge on 1 electron is what?
1.6 into 10 to the power 19.
1.6 into 10 to the power minus 19 coulomb, right? So charge on 1 mole of electron,
That into 6.0
into 6.
into 10 to the power 23.
so this into Na, correct? Into the Avogadro number. So this value is coming out to be 96500 coulomb, right? When you multiply this by this, you won't get exactly this, you'll get 964 something. But when you take this charge on 1 electron is 1 point up to 3 decimal digit, 1.63 something we have. So up to 3 decimal digit if you take, so it is approximately comes out to be this. So this coulomb is defined as 1 Faraday of charge. 1 Faraday of charge. Right? So 1 Faraday, F, it is just a unit of charge, Faraday, is 96500. This is very important. What is the point line you have written just now before this? Tell me. Mass deposited when 1 mole of electron passes through the electrolyte for 1 second, then
Equals to the equivalent mass.
equals to the equivalent mass, right? So any electrolyte if you have, if you allow 1 Faraday of charge, if passes through, then the mass deposited is equals to what? The equivalent mass of that particular metal. Suppose we have silver ion. Silver ion, 1 Faraday of charge you passes through, then the equivalent mass of silver, that is 108. 108 gram of silver will get deposited. Right? Oxygen gas, 1 equivalent, that is 8 gram, that will get evolved or deposited. Right? So this is very important, that 96500 coulomb gives you the equivalent mass of that substance. Okay. Now, if Q is equals to, just we are trying to use this, data. Q is equals to 96500 coulomb. What is M then? M is equals to the equivalent mass, correct? That is E. Now, when we substitute these two in the previous relation, we can write E is equals to Z into 96500. So what is Z? E divided by 96500. So this D, if you substitute in the first relation, which is M is equals to ZIT, EIT by 96500. This is the relation of mass with a given amount of charge. One thing you always keep in mind, that this this T must be in second here. Always will take time in second for calculation. Did you understand this?
So E is the atomic
equivalent mass.
Okay.
Equivalent mass. Now suppose we have Zn plus 2. Equivalent mass का concept you should know here, right? Zn plus 2. Zn plus 2, the equivalent mass is what? It's atomic mass.
Atomic by 2.
By 2. So this information we have done in grade 11. Like you see this chapter, why it is a bit complex, because we are using the concept of different chapters here. We are using the concept of ionic equilibrium in electrochemical cell. Now we are using this concept of equivalent weight that we have already discussed in the other classes in 11th grade, right? So if nothing is given, you write down the half cell reaction. The number of electron exchange is nothing but the n factor for this. And atomic mass by n factor is what? Equivalent mass. Right? So little bit of idea of equivalent mass if you have, you won't get any problem over here. You will understand that what should be the equivalent mass here. Did you understand this? So whenever you have charge and the amount deposited, you just recall this line, that 1 Faraday when passes through, 1 equivalent mass has been deposited. Right? 96500 coulomb is equivalent to the equivalent mass of that particular substance. Now, based on this relation only, we have Faraday's second law. What does it say? You see here, if we what is this? IT by 96500 is what? It is a Faraday. This is IT by 96500 is nothing but the charge. Right? So if the charge is same for two different electrolytes, then the mass deposited will be in the ratio of their equivalent mass. See, what I'm trying to tell you is M is equals to E into IT by 96500. Right? So this is what, if you see, this is the number of Faraday, yes or no? 96500 coulomb is 1 Faraday. So number of Faraday in this coulomb is IT by 96500. Right? Or we can say it is just charge. 10 Faraday, 100 Faraday, whatever it is, but it is charge, right? So this charge is equals to what we can write? Charge is equals to, we can write M by E. Yes or no? M by E is equals to what? M is the mass, E is the equivalent mass. So this is also number of equivalents, correct? Yes. Anyone is doubt in this?
Number of equivalents.
Sorry, number of equivalents.
That's just n factor there.
M by E is number of equivalents, right?
Yes, sir.
Sir,
Huh.
sir, if I add Fe3 plus to Fe2 plus, then the n factor would be 1 or 2 because there's only one electron exchange.
What?
If I add Fe3 plus and then I make it Fe2 plus, then for
One
Fe2
electron,
plus, the n factor would be 1. Okay.
one exchange.
Okay, sir.
Okay. Now suppose we have two electrolyte here. Electrolyte 1 and electrolyte 2. Two different electrolyte we have. But the charge, same amount of charge passes through two different electrolytes from this one and this one. Then what is the mass deposited here? Here we have M1, its equivalent mass is E1. Here we have M2, its equivalent mass is E2. So since charge is same, so can we write down the charge for two different electrolytes is equals to what? Here it is M2 by E2, this one. And this side what we can write? M1 by E1. So further the relation is what? M1 by E1 for one electrolyte is equals to M2 by E2 for the another electrolyte. Did you get this?
Yes, sir.
So what if you write down this particular relation in the statement, we say when same amount of charge passes through two different electrolytes, then the mass of different substance deposited at different electrode will be in the ratio of their equivalent mass. Can we say that M1 by M2 is equals to E1 by E2? Yes or no, guys? So this statement, this relation, we call it as Faraday's second law. So like I said, it is just the, it's the same thing that we have discussed in first law, but this statement, we call it as second law. If you want, I can, dictate, you will write it down, but this is the statement here. For equal amount of charge passes through two different electrolytes, okay, the mass deposited at various electrode will be in the ratio of their equivalent mass, respective equivalent mass. We can also say equal charge gives equal number of equivalents. Equal charge gives equal number of equivalents. Any doubt? Have you heard about a term called current efficiency? Yes? Have you heard about a term called current efficiency? You know, efficiency you must know, right? If I say, if I allow this, 100 ampere of current, if I allow 100 ampere of current from an electrolytic solution, but this current efficiency is 50%, then what is the effective amount of current is there? 50 ampere. This is current efficiency, right? Effectively, what current is passing through? Suppose for an electrolysis, we required 100 ampere of current. For a particular electrolysis, we required 100 ampere of current for a certain period of time. And the current efficiency is given, that is 50%. Then what should be the amount of current we allow to pass through so that the electrolysis takes place? Sorry?
So 50% efficiency, right?
Efficiency, and we need 100 ampere of current
So
for
200.
a particular
200 amperes.
200 ampere we need to provide, right? So this current efficiency based question they have asked in JEE many times. You don't have to do anything. Whatever I is given, correct? According to the current efficiency, you find out the net value of I, which is effectively passing through. Agar, if I say here 10% is the current efficiency, right? Then you are providing 100 ampere, but effectively 90 ampere is only working, right? So we'll do the calculation based on this, not on 100. Are you getting my point?
Yes.
Okay, I'll show you some questions on this, okay, which has been asked in JEE exam. You do this question. It's
So will
easy.
it be
You can
90 or 10?
current
90 will go
efficiency is
unused.
10%. So it is 90 will go unused. We have 10 ampere
10
only
is efficient. Yeah.
because only 10% is the efficiency, no? So only 10% will use. Okay. So you solve this question. Just a second. In this current, we'll also do this, but one current efficiency question. This one is also very good question. I want you to show the question of current efficiency. Current efficiency question is not this. This is not the question. This is the question. Achha, you do this, then I'll show you the current efficiency. Do this one first. Just you need to know that relation m is equals to EIT by 96500 and that one point. That one mole of electron passes through, then one equivalent of the substance get deposited. Just one line gives you all the answer in this.
So manganese mass.
Sorry?
What was the mass of manganese?
87. No, just a second. I think it's
Not
87.
required because you can just do m
Yeah,
by
we don't need it. We just need N.
Okay.
Mass is 87. Right? The value of current efficiency only you need to find out.
So is it 8%?
8.
Yes, sir.
No, not even close.
Oh, yeah, I think I messed up 10 powers.
Check your calculation.
So 82%.
Sorry?
82.
22. What are you doing?
No, sir, 82%.
82. No, it's not 82 also. It's 95%. What are you doing? Tell me.
We're just using the formula.
See, in this question, I is given already, right? But what you are providing this 27 ampere of current, but what is being used, that we do not know in this process, right? So we need to write down the relation M is equals to ZIT, and from there you find out I. That I must be lesser than 27. Then only we have, current efficiency is not 100% in that case. If all the current has been used, it means that efficiency is 100%, but that is not the case since the question is about current efficiency. So you use M is equals to ZIT, find out I from that. Okay, and then that I divided by 27 into 100 is the efficiency. Are you getting in? What is N factor you are taking here? I think you are making mistake over there.
2, N factor is 2.
2.
2. That's right. 2 is correct.
So I got
Then
95.
nothing is 95 is correct. Yeah.
So you could just multiply it with efficiency on that side and then like put the same equation multiplied with efficiency.
That also. So if in the question I is given and it is mentioned that its efficiency is 60%, then you have to take 0.6 I for the calculation. Are you getting it?
So it's I'm getting like 94 point some stuff.
So 95% is the correct answer we have. So here you see, I think I should explain how N factor is +2. Then there's nothing. You just have to use the formula. See, Mn +2 converts into what? MnO2, right? So you just have to balance this. Oxygen will balance by 2H2O, then 4H plus. Then you balance the charge. We must have here 2 electron. Number of electron exchange is 2. Hence, N factor for this reaction is 2. Correct? Now, we can write M is equals to E by EIT by 96500. That is the only relation we have. I we need to find out. So I is equals to M into 96500 divided by E into T. Now M by E is what? Is the number of equivalents, right? It says 24 hours, 1 kg of MnO2. 1 kg of MnO2 means 1000 gram. So mass is 1000 gram, right? Time we have to convert in second. Okay, time we have to convert in seconds. So what we can write? 87.
86 is
24 into 3600.
86,000.
Yeah, so it is 1000 into 96500 divided by 87 by 2 into 24 hours. So 24 into 3600. You will get this I as lesser than 27, 25.67 approximately you get ampere. So what happens? We are providing 27 ampere, right? But what is being used? 25.67. So current efficiency is what? This into this. Around 95% you get approximately. Understood this? This one you try. One different type of question you see. I think this one. This one you try. This one is also easy. You think about it, you can do this question.
So for the last question, where did we use n is equal to 2?
Here, this two.
Oh, okay.
Equivalent mass is atomic mass by n factor.
Okay.
So what's the atomic mass of silver?
108.
Silver
108.
108.
Okay.
So is it 272 grams?
Yeah, that's what I got.
Yes, sir.
272.
Oh, we have to find the area, not the mass.
No, that's the
It's
second.
hard. The first part of the question is.
Oh yeah, 270. Yes.
Yes, mass is correct.
The area I got 10,200 approx.
Yeah, same. 10,001.
Yeah, yeah.
200, yeah.
10205 it is given. So what do we do? It's very simple.
Volume is equal
Only-
to mass by density.
Yes, only one step ahead you have to go into this, right? I'm going from the from the back. You see, density is given. Density is mass by volume. Volume we can write what? Area into the thickness x. You see, the thickness is given. Area we need to find out. Density is already given. Mass we do not know, but mass we can find out from the formula, and that is m is equals to EIT by 96500. So your answer for this question is A is equals to EIT divided by 96500 into X into density of substance. Correct? No?
Yes, sir.
E is what? Silver plus 1 oxidation state is given, so 108. I is given 8.46 ampere. Suppose here it is given that its current efficiency is 40%. Then we'll say we'll take 8.46 into 40% of it, right? 0.40. That is what one change you need to do. So I is 8.46. T is given 8 hours, so 8 into 3600. X is given 0.00254. D is already given 110.5. Everything you substitute and calculate, you'll get the area.
So
Okay.
what is the answer supposed to be?
Answer is,
1020.
I'll write down, mass is, exact value I'm giving you, 272.178. 178 gram is the mass, and area is 1.02 into 10 to the power 4 centimeter square. This is the answer given.
Okay, sir.
Okay, you want me to do this? Just you need to substitute and get the answer. There's nothing much. Okay. Now you see, sometimes what happens, there are suppose some gases, some gaseous species are evolving here. You see, now see how they frame the question. Some gaseous species are evolving, correct? And the entire thing is at STP. And they'll ask you to find out the volume of the gases evolved. Did you understand? Condition is at STP. Any gas is evolving. They'll ask you what volume of gas evolves. How do we do this? Any idea?
So we find the mass and then we divide it by the molar mass and we get number of moles, and then with that we can get the volume.
Yes. So basically mass to mole, and we know 1 mole at STP is what? 22.4 liters. So given number of moles, how many liters? That is what it is. Okay, so that's why I said this portion of this chapter is very easy. Okay, if you get questions from this, you won't get any difficulty in solving this. Little bit of idea you should have how to calculate the equivalent mass, because that is the only thing where you can make some mistake if you're not comfortable with the concept of equivalent mass. Okay, so the quick revision of equivalent mass that we have done last year is most important. I won't say you go there and revise that chapter, then you start solving this. Solve the question here only if you're stuck, and then we can go back and revise. Okay, I'll give you one question on this, the volume related question. Chalo, we'll see two questions here. Write down. Or let it be, I'll just project this. Give me just 30 seconds. Try this one. 0.42. No. 0.85. Yes, it's correct.
I forgot what 500 ml.
No, it's not 0.93. See, you find out when electricity passes through, right, then what is the number of equivalent, which is given here, 2 hours, 2 ampere, 1 hour, right? So what is the number of ions or the equivalents get deposited? That is, you have to remove, right? And that you subtract, find out the net number of equivalents and the normality.
Well, I'm getting that number is 0.07.
That's what even I got, yeah. Then subtract from 0.42. So you have 0.5 normal initially, right?
Just a second, just a second.
You have 1 initially.
But you have 0.5 equivalents because it's 500 ml. I mean,
Yeah. Oh yeah. Yeah. Then it's 0.85.
Yes. Tell me.
Nothing, sir. I didn't see that 500 ml. Sorry.
Okay. So just you need to find out the number of equivalents left in the solution, because ions from the solution only, it is getting deposited onto the electrode. So obviously the number of ions in the solution is decreasing. That will change the concentration term, normality or molarity, right? So you see in this one, what is the initial number of equivalents? Number of milli equivalents, because volume is given in ml, so number of milli equivalents initially present equals to 1 normal into 500 ml. So 500 milli equivalent, right? Milli equivalent initially present. But when this electrolysis takes place, okay, so what is the number of equivalents removed from the solution? And that you need to find out m by E. We have discussed that. M by E is nothing but the number of equivalents. So for I amount of current you see, we can write down again the same relation. M is equals to I E I T by 96500. So the number of equivalents from here, if you find out, it is M by E. Is I is 2, T is 3600 by 96500. This number of equivalents has been removed from the solution. What is this value? Could you tell me?
0.074.
071.
74.
74 milli equivalents have been removed. So what is left? 500 minus 0.074. And normality is what for the solution? Is this value divided by what? Oh, I have made one mistake. This is equivalent, no. So it is 74 milli equivalent, is it?
Yes, sir.
Because this is milli equivalent. So it is 74 equivalent we can take approximately. So normality is this minus 74. So that will be 426 divided by volume is 500 ml. This equals to
0.85.
no. This is the answer for this question. Got it? So this is it for this particular topic. Volume related questions are very easy. I am very sure that you can do it easily. One question of volume related we'll see, and then we'll take a break, and then we'll start the conductance. We'll start with the conductance of electrolytic solutions. Write down one question here. Write down during electrolysis, during electrolysis, 4.5 gram aluminium, 4.5 gram aluminium get deposited at cathode from Al3 plus ion. Means in the solution we have Al3 plus ion present. So during electrolysis, 4.5 gram aluminium deposited at cathode from Al3 plus ion. Find out the volume of H2 gas evolves at cathode from H plus ion, right? The condition is STP. That is what we have to assume. The condition is STP. Means what is the question? I have given you in short, okay, the entire unimportant thing I did not tell you. I'll just tell you the data what it is. We have Al3 plus solution and we have H plus solution. From Al3 plus solution, aluminium is getting deposited, 4.5 gram is the data given. H plus H2 evolves, right? So you need to find out the volume of H2 evolves for the same charge when passes through. Chaitanya, it's wrong.
So is it 11.35?
No, Akshit got the right answer. Not 0.5 gram. We need to find out volume. Kirtan. We need to find out volume.
Is it 5.6?
5.6 liter is correct. What is the equivalent mass of aluminium?
9.
9. 27 is the atomic mass. Al3 plus is the ion, right? So 27 by 3 is 9. So you write down the mass of hydrogen divided by the mass of aluminium is equals to 1 by 9, the equivalent mass of the two. All right, mass of aluminium is given 4.5. So calculate the mass of hydrogen from that, and then number of moles, and then volume. See, it is actually the second law. see the mass of hydrogen divided by the mass of aluminium is equals to the equivalent mass of the two. So this means this value is 1. We know the equivalent mass of hydrogen is 1. For aluminium, it is 27 by 3 because Al3 plus charge is there, right? So it is 1 by 9. So now the mass of hydrogen is equals to mass of aluminium is 4.5 into 1 by 9. So that would be 0.5 gram. So 0.5 gram, the number of moles equals to what we can write? 0.5 divided by 2. So that is 0.25 moles. So 1 mole is, I'll write down directly. Volume is equals to what we can write?
22.5 by 4.
0.25 into 22.4. So that will be 5.6 liter. Okay. So we have discussed all kind of questions, little bit of information if you have how to calculate equivalent mass and other stuff. You can do this question easily. Just one formula we have, only one formula. That is M is equals to ZIT. Z is equals to E by 96500. Only one statement you have to keep in mind. 1 mole of electron, 1 Faraday of charge, equivalent mass of that substance will get deposited. With this, find out the charge. So 1 Faraday gives this much gives what? This much coulombs gives this much coulombs gives what? That is what you need to do, unitary methods. Understood? Clear, all of you?
Yes, sir.
Fine. Guys, so we'll take a break now. We'll start at 4:50. Okay? Yeah, take a break. Hello. Hello.
Yes, sir.
Yeah. Okay. So the next thing we have to discuss here is about electrolytic conductors. Heading you right down the last part of this chapter, electrolytic conductors. See, when we talk about conductors, okay, mainly we have, excuse me, mainly, mainly we have two types of conductors. Okay, conductors are classified into two categories. Okay, one is electronic conductors. Electronic conductors, and other one is electrolytic conductors. Electronic conductors, we also call it as metallic conductors. Metallic conductors. Okay. Our focus will be on the electrolytic behavior of an electrolyte, electrolytic conductors. This is our focus. Okay. But since we are discussing about conductors, so little bit we'll discuss about this also, so that we can understand the difference between the two. Okay. The first difference we have here, that electronic conductor shows conductivity because of the movement of electrons. So here we have movement of electrons, hence we call it as electronic conductors. But here we have movement of ions, not electrons. Movement of ion. Electrolytic conductors, as I told you, the movement of ion is the reason of their conducting behavior. Okay, but here electrons moves from one point to another point. That is a major difference. Example of electronic conductor, we have graphite, many metals we have. Okay, we have other examples also. Any metal we can take, certain minerals also some example we have of electronic conductor. Graphite is also conductive in nature because of one free electron present onto it, right? Electrolytic conductors, we have many examples. We can take any strong electrolyte, weak electrolyte, salt, any examples we can take, right? So examples of electrolytic conductors are, I'm sorry, examples, we can take strong electrolyte, strong acid or base, weak electrolyte also, and salt also. It's salt. Okay. Then we can classify this as strong acid, weak acid, strong base, weak base, salt of strong acid, weak acid. Many examples are there that we already know. Okay. The difference between the metallic conductor and electronic conductor, the and electrolytic conductor. The first difference I told you, that is the conducting behavior. What is the reason for their conducting behavior? One is electrons and other one is ions. That is the one major difference. Okay. another thing what happens, this electronic conductor conducts electricity without any decomposition. Metal won't decompose, right? Electrons moves from one point to another point. So there is no decomposition here. So right on here, it conducts electricity without decomposition. But in this, what happens? When you allow electricity to pass through, right, then electrolytes dissociates, right, into its ions, right? And basically electrolyte, suppose we have Na2SO4, it dissociates as Na plus and SO4 2 minus, and hence it moves, right? So here what happens, decomposition takes place. Here write down, conduct electricity with the decomposition of the substance. Now the one very important behavior here, write down in metallic conductor, as temperature increases, conductance decreases. As temperature increases, conductance decreases. Here, conductance increases with temperature. This is very important. Conductance increases with temperature. Okay. So you see, why electrolytic conductors shows conductive behavior? Because of obviously the movement of ions. Hence, there are two factors here which decides the conductivity of electrolytic conductor, right? The basic thing is movement of ions. So the conducting behavior of the electrolyte will be more if the ions can move with more ease and their ionic mobility is high. With high ionic mobility, conductance, electrolytic conductance increases, right? With more number of ions will be the movement, more electrolytic conductors, and size of ion is also a factor, right? So we have three factors here which uh, which affects the conductive behavior of an electrolyte. One is the number of ions, movement of ions, and then size of ions, right? We'll discuss these things later also. What happens with increase in temperature? So for two different electrolytes, we have two different reasons here. For with increase in temperature, strong electrolyte has a different reason, and weak electrolyte has different reason. However, in both cases, whether it is strong or weak, conductance increases. Conductance increases. So what happens in strong electrolyte as temperature increases? Write down, as temperature increases, the interionic attraction decreases for a strong electrolyte. The interionic attraction decreases, hence ions can move with a faster rate. Right? So more temperature, more movement of ions, lesser will be the attraction, hence ions can move with a faster rate, more will be the conductance.
Why doesn't
Weak
that take
electrolyte,
place in metallic conductor?
sorry?
Why doesn't the same thing happen in metallic conductor?
We'll discuss electronic metallic, we'll also discuss. Let's finish first electrolytic part. Okay, we'll come back to that. Okay.
Yes.
Weak electrolyte, you write down. Write down, as temperature increases, the dissociation of weak electrolyte increases. More ions produces here. Dissociation of weak electrolyte increases, more ions produces, hence conductance increases.
So could you repeat it?
So in weak electrolyte, what happens? First of all, weak electrolyte won't decompose completely. So when you increase the temperature, decomposition of weak electrolyte increases. Means it produces more number of ions. More number of ions, more will be the movement, more will be the conductance.
So,
Yes.
so could you repeat the strong electrolyte point? I got
Strong
this.
electrolyte, as temperature increases, interionic attraction decreases. Interionic attraction decreases, conductance increases. All of you are understanding this, no? Interionic attraction means the attraction among the ions. Positive, negative ions are there. So attraction among these ions are interionic attraction. Okay. So if they move with a faster rate, the attraction will be less, hence more conductance. So this is the two different reasons we have for two different electrolyte, but the result is same for both. Conductance increases with temperature. Correct. Now what happens in this metallic conductor? Write down, due to increase in temperature, due to increase in temperature, the vibrational energy of the positive ions, because conductors in metal, what happens? We have metal ions and electrons, right? So metal ions, the vibrational energy increases. It starts vibrating around the mean position with a very fast rate. Okay, the vibration increases. So with that increase in vibration, it offers resistance to the flowing or moving electrons, right? So write down, as increase in temperature, the vibrational energy of the positive charge ions or metal ions, you can write, increases, which offers resistance to the flow, offers resistance to the flowing electron, and hence conductance decreases. One more term here, the positive ions that you have written, metal ions, we also call it as kernels, the another term for this. So in some book you'll see that they have written the vibration of kernels increases. The vibration of kernels increases and hence conductance decreases. So this means positive ions only. Okay, same thing. So what is the reason of resistance here? Could you tell me?
Vibration of kernels increase.
Kernels, that positive ions, right? The positive ions offer resistance. That is the another point. The reason of resistance is vibration of kernels. And here the first of all, you write down this. The reason of resistance is the vibrating kernels. And in electrolytic conductors, the resistance is due to the interionic attraction plus the viscosity of the solvent.
So can you repeat for electrolytic?
Electrolytic conductors, the resistance reason is interionic attraction plus viscosity of the solvent. The solvent is more viscous, the movement of electrons won't be there, right? Conductance decreases. Correct?
Yes.
Okay. So this is the reason. So mainly, like I said, we have to focus on electrolytic conductors. But this reason, they ask this reason in board exam also sometimes. Okay. Temperature relation is most important here. You will get objective questions also on this temperature relation, reason of resistance, other things, right? Okay. So electrolytic conductors we have to focus on. Now we use various terms here for the electrolytic conductors, right? Like we have, in metallic conductors, we have resistance there, right? Resistance. We have resistivity there, right? Similarly, here also we have terms. Like there we have resistance, here we have conductance. There we have resistivity, here we have conductivity. Are you getting it? Right? So the various terms that involves in this, write down the next point. The first term we are going to see here is electrolytic conductance. Electrolytic conductance. There are 4 terms we are going to discuss here in this section, okay? And again, I am telling you one thing, that here you must take care of unit, okay? Because there are different terms given in different books, okay? But their unit will be same. So unit actually gives you the idea that what term it is, right? We have different symbol also for one single term, right? Unit you must take care of. Even in the question, right, you will get the idea what term is given. You'll get the idea from their units itself. Okay, give me 1 second. Yeah. So you see electrolytic conductance, it is represented by the symbol is, in some book they'll write Z, capital G, or C. Both are electrolytic conductance. Okay. Mode conductance, mode will be the tendency of electricity to pass through it. Okay, so write down into this, it facilitates the flow of electricity through the conductor. Through the conductor. Represented by C or G. This conductance C it is defined by 1 by resistance, inverse of resistance, R. What is the unit of R?
Ohm.
Ohm. What is the another term? Unit of R? Don't know. Resistance is ohm, right? So conductance is what?
Siemens.
We can write Siemens represented by S simply. This is also mho we can write, or we can also write ohm inverse. All 3 are the same thing. Like I told you in the beginning, units are very important here. Okay, if you keep this unit in mind, okay, you won't get confused what terms is given. Okay, so this is my suggestion. You must take care of unit in this particular. So this is electrolytic conductance. You see, conductance is the inverse of resistance. Okay, next up. Next is conductivity. Conductivity, or we also call it as a specific conductance. Okay, this conductivity or specific conductance is represented by a letter called kappa. Looks like K, but it is not K. We call it as kappa. K-A-P-P-A, kappa. Okay. Now you tell me one thing here. Have you seen this expression?
Yes.
What is this?
Resistivity is equal to rho L by.
Resistance is equals to rho L by.
Yes.
R is the resistance. Okay. R is the resistance. What is rho? Rho is the resistivity. Right? R is the resistance. Rho is the resistivity. What is L by A?
Length by.
Length by.
Length by area, which we call it as cell constant. Okay. Yes. Correct, Kritika. This L by A is cell constant. Okay. And for a given cell, this value won't change. Okay. It is cell constant. And cell constant is represented by this Z star. This is cell constant. This rho is the resistivity. And this R is the resistance. You must have done this in physics, right?
So before we've done.
Okay, resistance. So how do we define resistivity? Resistivity is the resistance offered by one unit length and unit cross-sectional area, correct? So this resistivity, we also call it as specific resistance, because if L and A both are unity, right? 1 and 1. So resistivity is nothing but resistance in that case. So for a given particular value, for a given particular case, resistivity is nothing but resistance. That's why we are calling it as a specific resistance also. So resistivity is the resistance offered by the the wire or whatever the thing we have there, but when it has unit length and unit cross sectional area. That is how we define. Okay. And one more thing I told you already, that conductance and resistance are opposite. Similarly, conductivity is opposite to what? Resistivity. Correct. So kappa is opposite to rho. If I write down this here, the conductivity kappa is opposite to resistivity rho. Okay, resistivity rho. Now if we try to find out the expression of it, what we'll do, we'll cross multiply this, right? We can cross multiply this. So we can write 1 by rho is equals to 1 by kappa L by A. So 1 by rho is what? 1 by rho is?
So 1 by ohm meter.
1 by rho is kappa. Sorry, why did I write kappa here? It is 1 by R now. Should be R, because we have crossed multiply this. This will come over here, this will come over here, everything is as it is. So 1 by rho is kappa, and 1 by R is what? 1 by R is conductance, that is C, or G we can write into L by A. So this is the expression we have. Okay. Could you tell me the unit of kappa?
Siemens per meter, ohm inverse, meter inverse, and mho meter inverse.
Siemens per meter inverse, centimeter inverse, depending upon the unit of this length, right? So this unit for kappa is S centimeter inverse or S meter inverse. We can also write ohm inverse, centimeter inverse, like that. Okay. So this is the formula of kappa. But with this formula, you can understand, you can solve the question. But to understand the other two terms that we are going to discuss after this, you should understand the definition of this. How do we define conductivity? So conductivity is what? For a given concentration, conductivity is the conductance offered by unit volume of a concentration of an electrolyte. Right? What did I say? Conductivity is the conductance offered by unit volume of any electrolyte of a given concentration. Did you understand this? Write down here, conductivity is the conductance offered by unit volume of any electrolyte for a given concentration. Is it clear? Means whatever electrolyte you have taken, you take one volume of that, right, of a given concentration. That one volume solution, whatever conductance offered by that one volume electrolyte is the conductivity of that. Understood this? Or we can also define this as we define resistivity. Means we can define conductivity. It is the conductance for unit length and unit area of the electrolytic cell. Right? So this is the definition of conductivity. Right? And concentration here, we generally take, because we have solution volume we have, right? So we generally take those concentration term in which the volume is involved. Right? Could you tell me what all concentration term we have where volume is involved? We have normality and we have molarity, right? So this conductivity, depending upon the concentration term, listen to me carefully, conductivity depending upon the concentration term, whether you take normality or you take molarity, depending upon these two concentration terms, conductivity is further classified into two categories, right? Let's see the two different types of this conductivity. Like this, it is not given in any book, right? Like this, it is not defined. You never see this, the conductivity is classified into two categories. This particular line you never see anywhere, right? But I feel this way you can understand the two different terms easily. Okay, otherwise there will be no connection. One by one we'll see the different terms, right? So you see here, conductivity, like I said, depending upon the concentration term, right? So concentration, like I said, there are two concentration terms in which the volume is involved, and those concentration terms are what? We can take normality, we can take molarity. Okay. So if you take unit volume, then the conductivity is, we have already defined, that is kappa, that is specific conductance. But what about if you take V volume of any electrolyte, right? So V volume of N normal solution if you take, then the conductivity offered by the electrolyte, we call it as equivalent conductivity or equivalent conductance. Okay, so write down here, V volume, V ml of N normal. N normal means normality is N. Of N normal electrolyte offers conductivity, offers conductance is called equivalent conductance. Equivalent conductance. This normality is there, so we'll talk about the equivalent. Okay. Molarity, similarly, if you define, VmL of, what we can write, could you tell me?
M molar electrolyte.
VmL of M molar. VmL of M molar electrolyte offers conductance which we call it as molar conductance or molar conductivity, molar conductance. Okay. Now, this molar conductance, it is represented by either mu or delta M. This is molar conductance, delta M. Equivalent conductance is delta EQ. Okay. Now you see here the definition. The 1 ml, the conductivity is kappa. So the VmL, the conductivity will be what? For 1 ml it is kappa. So for VmL it is
E kappa.
kappa into V ml. No doubt. This is also kappa into VmL. Right. So if it is N normal electrolyte, then this kappa into V is nothing but the equivalent conductance. If it is M molar, then this kappa into V is nothing but molar conductance. Okay. Now you see N normality means what? Further, it means we have N equivalent in 1000 ml solution, yes or no? Can we say that? Normality is N, it means what? N equivalent is present in 1 liter of solution. That is what it means, no? Yes.
Yes, sir.
So 1 equivalent present in how many solution? Volume of solution? It is 1000 by
N.
N solution, right? So this thing, why I have written this, because the equivalent conductance here is, it is the conductance offered by conductance offered by conductance offered by 1 gram equivalent or 1 equivalent simply. Okay. So 1 gram equivalent of VmL, whatever conductance is offered, that is equivalent conductance. Here also you see I have written VmL of N normal electrolyte offers conductance is called equivalent conductance. But here the electrolyte must have one equivalent, then it is equivalent conductance. Okay. Here also VmL of M molar electrolyte offer conductance, molar conductance, but here we have 1 mole. The electrolyte must have 1 mole here. Correct. So now 1 gram equivalent, the conductance offered by this is equivalent conductance. So what is the volume of 1 gram equivalent? That volume we can find out what? N equivalent is 1000 ml. So 1 equivalent is 1000 by N ml. So this is nothing but, can I write down this? Is this volume is nothing but V that we have assumed here. Can we say that? See, VmL means what? N normal, suppose N is the normality, right? VmL of any electrolyte has 1 equivalent, right? Has 1 equivalent present into this, right? So if normality is N, it means what we can say? N equivalent is present in 1000 ml solution. So what is the volume of one equivalent? One equivalent, the volume is 1000 by n. Means if you write down the expression in terms of normality, this volume you have to replace with delta equivalent is equals to kappa into 1000 divided by what? Normality of the solution. Is it clear? Any doubt you can ask me? What?
Yes, sir, understood.
It's clear, no? See, again, I'm telling you, it is not that confusing. Just you see this thing, equivalent conductivity, you can understand one simple line. It is the conductance offered by 1 gram equivalent of any electrolyte, right? Equivalent conductivity means 1 gram equivalent you have to talk. Molar conductivity means 1 mole you have to talk, right? So 1 gram equivalent, if the volume is V, then delta equivalent is what? Kappa into V, right? If V ml of any solution has n normality, right? So n normality means what? N equivalent is present in 1000 ml of solution. So one equivalent, the volume of one equivalent is what? It is 1000 by n. So this volume is nothing but the volume of one equivalent, and that is what I assumed here. VML is the volume of one equivalent present in a solution whose normality is n. That is what we have assumed. So this V I can easily replace by 1000 by n, hence the formula becomes this. Clear? Easy? Similarly, could you tell me what is the formula of this we get? Molar conductivity?
So it's just 1000 by n.
1000 by n. So this will be kappa into 1000 by the molarity. So this is what the difference we have between the two. If you are talking about equivalent conductance, you have to take normality, molar conductance, you have to take molarity. That is it, nothing much you have to do. I hope all of you have understood this, the definition, but you will get formula based question into this. You won't get any theoretical or concept over here. Just formula based question. You see, you know the formula, you can do the question easily. But I'll suggest whatever the question given, write down the data first. With data you will understand that what you have to do. Okay, like I said, the constant, the terms, the units are very important to this. So could you tell me the unit of this one? See, unit of this is what I'll write down here. Unit for equivalent conductivity, kappa is what?
1
S
by ohm, 1 by meter.
centimeter inverse, right? And is 1000 ml. Ml is what, nothing but centimeter cube. Normality means it is the number of equivalent, so equivalent inverse. So unit is S centimeter square equivalent inverse. This is the unit of equivalent conductivity. Similarly, molar conductivity, the unit will be S centimeter square mole inverse. That is it, nothing much. Clear? No doubt? I'll show you one question on this. Okay, see this question. Done? See, no, cell constant is G star actually, not Z, not Z. Where is Z here? Cell constant is L by A. L by A is Z star. It is represented by G star. And if the cell is same, L by A won't change. That will be constant.
So when you add two solutions together, does their conductance just add up?
I'll come back to this. Wait. We'll see one question on this. Okay. After this, we'll see one question on the same concept. Okay.
So, because I need it for this one only. They're adding two solutions together.
Oh, you are talking about this one.
Yeah.
No, we are not adding two solutions. See, the question is what? The resistance and conductivity of this KCl solutions are this given, right? When filled with this, it does not mean that we are mixing the two, right? The resistance conductivity of KCl is given when it is placed um, in a cell, right? Whose cell constant is something that we do not know.
Okay, sir.
In the same thing, if you place K2SO4, then what happens? That is what it means.
Okay, sir. Yes. No.
You're not mixing the two. For
Yes.
mixing, we'll have a question. I'll discuss this after this. Okay.
Yes, sir. So could you
Okay,
give
all of
like
you guys.
1 minute more?
Right. All of you guys, we are not mixing K2SO4 and KCl. Okay. It's like KCl in a cell it is present, and in the same cell if you add if you put K2SO4, then what happens? What is the answer, Param?
So for which one?
First one, what is the cell constant value?
0.228.
Okay. B.
So wait 1 second.
I got 7.037 into 10 to the power minus 4.
7 point.
I got 6 point, that same thing, same power of 10.
I think you have missed half somewhere, Param.
Oh.
See, okay. You see, what happens here, the first question is you need to find out the cell constant, correct? And cell constant won't change if you change the electrolyte because cell is the same, right? We are just changing the electrolyte. So cell constant won't change. So with the help of data given for KCl, we can find out cell constant, and that cell constant we can use for all these B, C, D, E, right? So first of all, you see, for KCl, the data given is, like I suggest, you always write down the data first. Then you'll understand what you have to do, right? So molarity is given for KCl. This is 0.02. Resistance is given 82.4 ohm. And what is this? You see, what is this unit? This unit for conductivity, right? So kappa is 0.002768 Simon centimeter inverse, right? Now, what we need to find out? Cell constant. We know the relation of kappa with cell constant. Kappa is equals to what? 1 by R
into cell constant.
1 by R into L by A. L by A is nothing but the cell constant. So L by A, which is G star, is equals to kappa into R, so 0.002768 into 82.4. Okay. Now, one more thing you see here, that if you need to find out cell constant by unit also you can do this, like I said in the beginning. You need to find out cell constant. So cell constant is what? Meter inverse or centimeter inverse. This should be the unit we should get. So how do we get this? How do we get this unit? If we multiply this K and this R, so that if you multiply the unit of K, that is Siemens centimeter inverse, into ohm, right? This ohm and this will get
So,
cancelled.
do we have to in this case, do we have to convert to meter inverse?
Why? Not required.
I'm asking. Oh.
No, not required. Not required. You can find out in centimeter inverse, right? So that's why unit gives you fair bit of idea over here that what we need to do to get the answer. Okay, so first thing, we get this cell constant. What is this value? 0.2281 centimeter inverse. So first we are done. A. Now since the cell is same, with electrolyte the cell constant won't change. So this cell constant we can use for all other calculations. Okay. B is what? Conductance of K2SO4 solution. Now conductance means what? Conductance is C or G inverse of resistance. Resistance is what? We know the value of resistance, 1 by
324.
82.4.
Why don't we take the other resistance here?
Yes, sir, we have to take the
K2SO4, right? So 324.
Oh, K2SO4. Oh, it's for KCl now. Correct. K2SO4 will take. So for K2SO4, the resistance is given 324. So 324 here we'll put. And this value is what?
0.003 approximately.
3.08 into the power minus 3. Means this is the value we'll get. 1 by 324. Now conductivity of K2SO4 is what? Conductivity is again kappa. So kappa we need to find out. So kappa is what? 1 by R into
G star.
L by A.
L by A.
L by A we have calculated already. 1 by R is 1 by R is C, 3.08 into 10 to the power minus 3 into L by A is what? 0.2281. Right? So this is
7 into 10 to the power minus 4.
6.84.
I was talking about when I got 6 point something into 10 power minus stuff.
6 point something you are getting.
So it's
the answer given is
7 into 10 power minus.
Yeah, that's one.
That's what the answer given. 7.04 into 10 to the power minus 4 Simon centimeter inverse. D. What is D? Equivalent conductivity. Equivalent conductivity is what? This equals to kappa into 1000 by?
Normal.
Since it is equivalent, so normality. So kappa we know. N value is what? 0.005. So all these values you need to substitute. 7.04 into 10 to the power minus 4 divided by 0.005. You'll get answer from this. E is what? Molar conductivity. Okay.
2 times of this.
Molar conductivity is what?
So it's just going to be twice.
Twice of this.
Yes, that also you can do. Because we know molarity, normality is equals to molarity into n factor. Right? So just twice of that. So this divided by molarity, you'll substitute this, you'll get the answer. The answer given here is 140.8 Siemens centimeter square equivalent inverse.
Yes,
and this one is almost twice of this. Yes, mole inverse. Done? Okay. So like we have relation between normality and molarity. Okay, so this relation, you see, we know molarity is equals to what? Sorry, normality is equals to what? Molarity into n factor, right? So you see from this what we can write, 1 by m is equals to 1 by n into n factor. Now if you multiply this with 1000 into kappa by m, 1000 into kappa by n into nf. So what is this term? Molar conductivity, and this term is equivalent conductivity. So delta m is equals to delta equivalent into n factor. This is another relation.
So could you show the previous page for 1 minute? Okay, thank you, sir.
Okay, so here you see, once you have calculated this, you can directly find out delta m with the help of this formula. Okay, with the help of this formula.
NF
Multiply
is,
by n factor. Huh?
okay.
N factor for K2SO4 is 2. It is a salt plus 2 and minus 2 charge. N factor is 2. You can multiply with 2. You'll get the answer. Got it?
Yes.
One more question you see. This one, it's not that tough. You can do this. But I would suggest this, you take it as a concept. Okay, what happens if you mix two solution, the effect on conductivity. When we mix two solution of different conductivity. Try this.
So what is alpha?
What we need to find out, we need to find out the resistance of this cell. No, the answer is 66.67.
So not answer. What is alpha?
Alpha, let me see the question. The resistance of solution A is 50 ohm. Where is alpha? Alpha, right? Acha, that is, or increase in, assuming there's no change or increase in, I think it should be kappa. Just a second. I think dissociation then, just a second, just let me read the question. The resistance of a solution A is 50 ohm. Okay. Alpha means dissociation, degree of dissociation. Means there is no dissociation in A and B.
So is the answer 33.33?
I think you have divided it by 2.
Oh, okay. And it's 66.66.
Yeah, it is 66.67. Last time you missed half in the denominator.
So I thought that, oh, okay. So that means that the conductivity, you have to take the mean of that.
No, not mean. We cannot say mean. It depends upon the volume. What volume you are mixing. Mostly when you mix this, see, initially you have A, some volume, correct?
Yes,
and
sir.
when you mix the equal volume, now the A is present in the twice of the initial volume, right? Because two things we are mixing, right? V and V you mixed. So now A is present in 2V.
Yes, sir.
B is also present in 2V. 2V. And since the alpha is not changing, right? So we can say the conductivity of A is what? It decreases, it becomes half because the volume becomes twice.
Yes, sir.
Concentration of ions decreases, no, by half.
Yes, sir.
So
Yeah.
its conductivity also decreases, becomes half.
And then even
Right?
B conductivity
For
becomes.
B also it is A. So if it is kappa A for A, kappa B for B. So after dilution or mixing A and B equal volume, it is kappa A by 2 plus kappa B by 2. So it is the average of both.
Yes, sir.
There are various factors. We cannot generalize this. That's why you see one condition they have given here, that alpha is not changing, because when you dilute it, the electrolyte has tendency to get dissociate. You keep on diluting, it keep on dissociating and gives more number of ions in the solution, right? Okay guys, you see here, first of all, we cannot generalize this, that what will be the kappa when you mix the two things, right? That's why the question is specifically it mentioned that we are mixing two equal volumes plus there's no change in alpha of A and B. Means there's no dissociation of A and B. Yes, it's correct, Ruchit. There's no dissociation in A and B. Okay. No dissociation in A and B. Because what happens in generally, that is what we have assumed, that dissociation is not there. What happens whenever you dissociate, whenever you dilute an electrolyte, right, whether it is weak or strong, okay, its conductivity increases, right? Conductivity increases. Why? Because on dilution, it has tendency to furnish more number of ions in the solution. More number of ions, hence more conductance, right? So if number of ions also changes here, then we cannot predict the kappa of that, right, in this question, because the data is not sufficient. Okay, we have different things, we can draw graph and all those things is there, but that those kind of stuff they won't ask in the exam. That's why one thing is for sure they have to fix, and they have fixed alpha over here, there's no dissociation. So if kappa is not see, if the ions, number of ions is not changing in the solution and you are mixing the two solution, it means obviously you are diluting it. This means you are diluting it. So if kappa A is the initial, sorry, if this is the initial conductivity of A, it is the initial conductivity of B, and when we mix two volume of A and B, so this of A, conductivity of A becomes this by 2, conductivity of B becomes this by 2 in the solution, the new solution here we have, where we have the volume twice of the original volume, right? So hence kappa is equals to, we can write, it is the new value is equals to 1 by R into L by A, that is the cell constant G star. This is kappa A plus kappa B by 2, 1 by R into LA. This we have to find out what is the cell constant. It is given in the question. It is not given, then we can find out the first set of data, right? The resistance of A is this, B is this. Both solution are taken in this full volume of this we have, okay? Okay. What is the cell constant here? One by R we need to find out.
Like it'll just get
Sir,
such.
R is okay.
That will be any one we can take, no? So kappa into is equals to 1 by R into the resistance is given. So we can take kappa.
Can we write it as either 100 into Ka or 50 into Ka or 100 into Kb?
So we can
Cell
access
constant.
Your voice is
thereby
breaking.
So can we write kappa A and kappa B substituting as 1 by
We can write down this. Kappa A is equals to 1 by 50 into L by A, right? and kappa B is equals to 1 by 100 into L by A. Oh, what I am doing, just a second. Resistance is given, same conductivity cell, so La is same, equal volumes mix, so it becomes average. Resistance of the mixture using the same cell. Okay, so we need to find out this R, right? So L by A, what we can write? It is 50 kappa A is equals to 100 kappa B. So kappa A is equals to twice kappa B, and we can solve this twice kappa B, so it is 3 kappa B by 2, and that will be 1 by R into LA. We can write, suppose 50, or LA we can, L by A we can write 100 kappa B, so it is 100 into kappa B. Okay, so kappa B gets cancelled. R is equals to 200 by 3 ohm, that is 66.67. This is the answer for this question. Okay, so obviously when we mix two different solution, their conductivity changes. Okay, conductivity changes because of the change in volume. Volume becomes twice, conductivity becomes half if there is no dissociation. But electrolytes gets dissociates when we dilute it. You must have remember one concept you have studied in ionic equilibrium, that you keep on diluting, the alpha value increases, right? And weak acid behaves as strong acid at on dilution. Remember 10 to the power minus 8 molar HCl, sorry, 10 to the power minus 8 molar CH3COOH, pH value is as equivalent to the pH value of HCl at some concentration. So at some concentration, if you keep on diluting the concentration of a weak electrolyte, its its conductivity increases because the dilution increases. Okay, on the basis of this concept only, we have the next topic. Okay, so next topic is what? If we keep on diluting, right, the electrolyte releases ions into the solution and conductivity increases, whether it is weak or strong. For both, the conductivity increases, right? For strong electrolyte, what happens? The increase has a linear graph, right? It has slope going upward direction. I'll show you the graph next class. I'm just giving you a little bit of idea today, right? For a strong electrolyte, the graph is going up linearly. Okay. For weak electrolyte, the graph is also going up, but it is a curve graph, like the logarithmic graph we have, those kind of graph, right? So, but the weak electrolyte graph does not touch the y-axis, right? Means on dilution, weak electrolyte does not give a limiting value. Means for weak electrolyte, on the basis of graphical method, we cannot find out the molar conductivity, right? Graphically, we cannot find out. One thing. Second point, you keep on diluting this, ions in the solution increases, right? So they have random motion in all direction, and there is very less interaction because volume is continuously increasing, because since you're diluting it, right? So volume is continuously increasing, it keeps on producing ion into the solution, and their ions are moving randomly in all directions, so it increases the conductivity of the solution, and you will get a concentration, you will have a point where the ions are completely free from each other. There is no interaction, there is no attraction, there is no repulsion. They are completely free from each other, moving in a solution and produce conductivity. That point of time where the ions are completely free from each other, that point we call it as infinite dilution. Okay. So at infinite dilution, the ions are completely free and they have a fixed contribution towards the conductivity of the cell, of the electrolyte. Okay. every ion has a fixed contribution towards the conductivity of that electrolyte at infinite dilution. So what is infinite dilution? What is that graph? How the conductivity changes on dilution? Okay, how do we calculate the conductivity of weak electrolyte at infinite dilution? Okay, that we'll discuss in the next class. So we are left with this infinite dilute concept, and then we'll have a titration graph, which we have already done in redox or ionic, but we'll see quickly, we'll go through it. That graph plus this, and that is it. Few questions we have to discuss, and then the chapter will be over. So next class, in probably 1.5 hours or 2 hours, we'll finish this, and then we'll quickly finish the reactions which are left in alkyl aryl halide. Okay, those reactions will finish. After finishing that, we'll start P block. Okay, that is what I am doing in the other batch also. So did you understand all the concepts discussed today? Okay,
Yes, sir.
I'll request you. You must solve the PDF. I have shared the entire PDF of electrochemistry. You check in your group, it is there. Okay, it's JEE means and advanced level DPPs are there. You must solve that. Solution answer key is given, right? So next class, I expect all of you must finish those assignments. Okay, I'm not expecting that you finished all, but at least 50% you must do. Okay. Okay, guys. Thank you.
Thank you, sir.
Thank you, sir.
See you in the next
Thank
class.
you, sir.
Yeah. Bye.
Thank you, sir.
Thank you, sir.
Sure.